Sorry, let me just get my screen configured. So good to see everybody. I have a quick announcement before we get started. I think you should have all heard from your MIT Posse deputy by now. So if you haven't or don't think you have, make sure to check your MIT email. When you do, make sure you respond if you haven't already. And let us know on Piazza if you still haven't heard or still have any trouble getting connected with them. All right, so with that, I want to dive in to our lecture today, where we're going to be continuing the process of talking about how compilers work and how our C code gets turned into what runs on an actual machine. And today we're going to dig a little bit more into the optimization process and try to develop at least a little bit of intuition for the sorts of things that compilers can and can't do when optimizing and compiling our code. All right. So we've been talking about compilers and the compilation process that takes us from C code all the way to assembly and machine code for a couple of lectures now. So we've seen this rough pipeline that goes from C through a preprocessor to LLVM-IR, which TV spent a lot of time showing you examples of last time, and then ultimately how it gets optimized and we generate assembly. So in the past two lectures, we focused mostly on learning about these different representations below C. So the LLVM-IR that our Clang compiler uses to represent programs internally, we talked about a lot last time, and the assembly code that shows what the actual processor will execute, which we talked about the lecture before that. And today, we're going to dig more into the optimization phase here that takes our initial program and optimizes it to be a lot faster. And we'll also touch a little bit on code generation that turns that into actual machine code. All right. Now, the diagram on this slide and the way we've been talking about this process and the different example program, compilers that we've been talking about and so on, have all been really specific to C code and x86 assembly. But one quick high-level point before we dig in, we're going to continue talking about C code and x86 assembly because that's our main focus in this class, and it's also, very, very common place to be working for performance engineering. But it turns out that the same LLVM core that's in our Clang compiler and that we're talking about now is also used by lots of different compilers today. So everything from C to Rust to Swift and Julia, to domain-specific languages like we develop in my group. Like one example is the language Halide. And LLVM, also has lots of different backends, not just x86. So for example, there's backends for ARM, like in your cell phone or actually future Apple laptops and stuff too. So basically all the code that runs on your iPhone or your iPad is compiled with the same LLVM compiler. And I think there's at least something like 24 official LLVM backends today for everything from lots of different standard processor architectures like the MIPS and PowerPC here to NVIDIA PTX, which is the virtual assembly for CUDA GPUs, NVIDIA GPUs, to other kinds of accelerators too, like Qualcomm Hexagon DSPs, and lots of embedded and other processors also. And the real value of LLVM is that it captures a lot of shared optimization. So things that apply to the low-level code ultimately output by all of these different compilers and relevant to almost any of these different processor targets. And that core is really embodied in this key piece, this key middle piece here. So many different compilers emit LLVM-IR, and there's lots of different backends, but most of the heavy optimizations, most of the kind of core rewrites that we think about wanting our compiler to do to our code are shared in this core LLVM optimizer, which all of these different front ends and back ends can rely on. And that's kind of, what we're going to get a little bit of a taste of today. Now, we're not going to cover everything that compilers can do. And in particular, there's also optimizations that are possible to do at the higher level of some of these languages. Before we get to the LLVM level, but this is a good overview of the state of the art of kind of the lower level optimization and compilation that you might see in anything from any of these languages to JavaScript to anything else. All right, so first I want to start with a little bit of motivation. So the compiler that we're studying is at the core of lots of different languages you might use. and it's a good representative of low-level optimizations in any state-of-the-art compiler pretty much. So clearly we care that it makes our code fast, but why do we really need to know what it actually is doing? Why should we study compiler optimization rather than just enjoying its benefits and getting on with writing code? Does anybody have any ideas? What do people think are some of the reasons we might want to look inside what the compiler is capable of doing? Go ahead and post on Slack. So if we know what the compiler does, we don't have to reinvent the wheel to identify effective optimizations. We can focus on optimizing what the compiler can't do. Yeah, so I think, when Sabrina thinks, maybe we can tailor optimizations for our code. That's actually more advanced than we're going to get here. But in general, we've seen already, we've gotten some hints that by looking at different levels of optimization, that the compiler optimization can have a really big impact on the code that actually gets run on our processor and therefore on its ultimate performance. And so if we want to be able to optimize and control performance, we need to be able to understand and work with that tool and be able to reason about a bit about what it's going to do to the code that we're trying to optimize. And in particular, we'd like to be able to focus our performance engineering effort in some sense on stuff the compiler can't easily do automatically. That's going to help us save work while still getting high performance. It's also going to make it easier for us to keep our code readable. Often things that may matter to optimize down at the level of machine code, you'd still like to be able to kind of keep abstract and simple at the level of your C code. And if it turns out that the transformation is a really simple mechanistic one that the compiler can just do, there's no reason we need to mess up our code and make it more complex, harder to read and harder to modify than it needs to be. But at the same time, compilers aren't perfect. They can't do everything. And so it's valuable to know and be able to kind of see and understand when they are and aren't able to do different optimizations so that we can try to make their life a little bit easier, work in collaboration with them, and get the most out of the ultimate code that we run. All right, so now let's start to look a little bit at what's inside our compiler. So, like lots of different machines or programs, the compiler is actually going to operate in a really mechanical way. So at a high level, it's a very simple thing. So at the most basic level, our compiler is just a sequence of passes that transform our code. So each of these passes is going to take in some LLVM IR, so the intermediate representation the compiler is working with. It's going to look at it, analyze it, see what it can figure out about it, and see whether it can potentially apply some edits that might make it faster. And then it's going to output that edited code to the next stage, the next pass in the compiler. And the ultimate pipeline we have is going to be a pretty long sequence of these different transformation passes. So what goes on inside each pass can be simple or complex, but the top level architecture really is that simple. Each pass just takes in some LLVM IR, tries to make it a little bit better, and spits it out to the next pass. And the optimizer as a whole just is a really long pipeline of these passes. Some of these passes actually might be useful to apply multiple times. So you might see them, at -03, I think we have something like 70 or 100 passes all stacked together. Some of them actually appear a bunch of times in that sequence. But ultimately, they're all going to run in a predetermined order that's -01, -03, et cetera, are all just macros for a big, long, fixed list of passes to run in a specific order. There isn't necessarily a perfect order. Different code might be better optimized by different passes run in different orders. But the standard optimization levels that we use are kind of an established order that the LLVM engineers have found tend to work pretty well most of the time on most programs. It turns out you can actually tell Clang and LLVM exactly which individual passes you want to run in what order. You can kind of explode your -03 flag, and instead of just asking it to do what it does by default, you can control every individual pass in the order they're applied. But we're mostly going to just trust that the compiler developers have done a pretty good job setting defaults, which is usually a reasonable idea. All right. So now this whole pipeline can get a bit complex, and it can be hard to understand exactly why a given optimization did or didn't apply to a particular piece of code. So, we can do what we did last time and a bit the time before and look at the LLVM-IR assembly that comes out after optimization. And that's helpful, but sometimes we might think an optimization should apply, but for some reason it still doesn't. But fortunately for us, the compiler actually can produce reports for many of its transformation passes that tell us about what they actually did and why. And indeed, I think you'll be using these to understand optimizations in homework 3, I believe, which will be coming up. So specifically with the Clang compiler that we're using, it gives us 3 key flags to request these reports. So first, there's this rpass flag, which is going to give us a report of which optimizations were successful. So which ones it was able to apply on what pieces of code. There's kind of the complement of that, rpass missed, which tells us which optimizations were not able to be applied. And then rpass analysis gives us a more detailed report of the analyses that drove some of those optimization decisions, some of the transformation decisions, like heuristics that might be reasoning about the relative benefit of different optimization choices, for example. You'll notice if all of these flags take a string argument, and that string is a regular expression with which we can ask to see reports on specific optimization passes that we're interested in. So we can give it, a list of a few passes that we're interested in learning more about. Maybe we particularly care about vectorization or something. Or if we just want to see everything the compiler does, we can pass pass .star as the string, which will match any pass name, and will give us a report on everything. All right, so that's cool. Maybe these reports are everything we need to understand how the compiler works. They'll just tell us what they did. But it turns out that the compiler is not really the best communicator. So this is an example report from, I think, an older version of some 6172 assignment code. So in this case, we passed the rpass and rpass analysis flags for .star. So we're asking for all the optimization passes that fired and all the analysis information that they can tell us about what they did. And, this is probably pretty overwhelming at first. If we look at this really hard, we can start to see some of what happened. So, this first instance, it's telling us like the line number, and we see a little printout of where it is in the source C code. It says it's hoisting a load because of this LICM pass. I think that stands for loop invariant code motion. And it looks like it's this, we've set the upper bound on some loop based on a lookup into some field of a structure. So we're dereferencing through a pointer here, and it looks like it's probably taking that dereference and load from memory, hoisting it outside, storing it in a local variable, and just using that local variable there. I think that's what's going on in that case. It's eliminating a load because of the global value numbering pass. I'm not quite sure what that means in this case. Here we can see some analysis results. So saying this method can be inlined into this other method on this line here, line 79. It estimates the cost of that inlining is some magic number 245, which seems to be less than the threshold 250. So indeed, it does do that inlining. That's the thing it tells us next. Okay, so, we can start to see what's happening here. There's a lot of information here. That's better than the compiler being a total black box, but it's obviously still kind of rough. And if you pass this, if you do if you want to get reports on all the passes on all the code in a non-trivially sized program, this is going to be a really, really gigantic report. So basically, there's some good news and some bad news here. So the good news is, the compiler can tell us a lot about what it's doing. It's not a total black box. And there's lots of, the most important transformation passes in LLVM that can report to us where they were successful. Many of them, like we saw that inlining pass, can also tell us about the analysis that they did and the conclusions they made about whether something was a good or bad idea, or whether it was able to figure out whether something was safe. So that's nice. So we don't need to just have telepathy and try to guess what the compiler is doing. But the flip side of that is that because this is basically a log of everything that happened inside the compiler, these reports can be pretty hard to understand. So they can be really long. They're reporting every one of 70 some passes on potentially every line or expression in a giant program. And maybe worse than that, they use lots of LLVM jargon. So, I was hand waving how you could squint at the example on the previous slide and have some sense of what it's doing, but really at some level, these things are often written more to be useful to compiler developers who want to, know why their analysis or why their pass did or didn't work in a given case. Because they're telling you, they're often written in terms of kind of what's happening inside the pass and how the pass itself works, and the jargon and keywords by which that pass works. So it's, there's a lot you need to learn about the language of the LLVM community in order to understand everything that comes out. Also not all the transformation passes generate useful reports. And the reports won't always tell you the whole story of why things turned out the way they did. So, it's a start. It's much better than nothing if you want to dig into a specific, particularly critical piece of code and understand why the compiler is or isn't doing different things. But it's, it only can ever get you really part of the way there, and even that can require some significant effort. So that's why we're going to be digging a bit further into how these passes work today, so that we can get a bit more context for understanding what the compiler did and, even just reading these reports. All right, so for the rest of today, I want to go through a kind of high-level overview of compiler optimizations and dig into some specific, relatively simple example cases to show how different types of code can get optimized. And we'll talk a little bit about optimizing some simple scalar arithmetic in a simple C function, talk about optimizing some code that uses more complex data structures, so like in C structs. And we'll look at how the compiler can optimize more complex control flow, including function calls and loops. And the end of these slides are some case studies of specific compiler optimization examples, the kind of interesting results in different cases and why different optimizations were and weren't able to apply, how to modify code to make them apply. But we're probably not going to get there, and I'm just going to post those online mostly as enrichment for people who want to kind of dig more and learn more. All right. So first, let's start out with a quick overview of the sorts of optimizations that our compiler is going to be able to do. Actually, any more questions so far? I want to stop here before I dig into the next section. Does anybody have any questions on what we've talked about so far? Actually, here asked something in the previous round. Did different compilers optimize for different uses? So I assume this was asking about all the different examples of compilers for different languages that feed into the LLVM ecosystem. At least that's one thing that might be asking about. In that case, it's definitely the case that Rust and C++ versus Swift versus Julia versus domain-specific languages like Halide, those languages are designed very much for different kinds of use cases. So C is designed to be relatively C and Rust are designed to be relatively close to the metal, to have a relatively thin abstraction over what the machine does, whereas at the opposite extreme, something like Halide is designed to have very high level but restricted abstractions that give the compiler lots of power to do larger scale optimizations. And you also see another instance of different compilers optimizing for different uses. The JavaScript compilers, for example, that run in your web browser don't use LLVM because they're optimized much more for speed of compilation in a real-time JIT compilation setting, whereas LLVM is mostly optimized for this sort of offline compilation that we do with languages like C, where you're going to invest a lot of effort up front to compile code ahead of time that gets run many different times. That's a good question. All right. So now back to a quick overview of the different compiler optimizations. So if you remember 3 lectures ago, Professor Leiserson gave us an overview, kind of a whirlwind tour in many tiny micro lectures of the Bentley rules, or our new reinvented Bentley rules for optimizing work. And this is a quick overview of a bunch of those different optimizations we saw. In that case, we saw that there were all the, lots of different kind of mechanical tricks and hacks to optimize different patterns in code. Now, a bunch of that stuff, at some level seemed kind of mechanical. So it seems like, maybe it'd be nice if the compiler could just help us apply all these sorts of optimizations. And indeed, that's actually kind of a good indication for what compiler optimizations, actually are going to do for us. But it turns out that, of the specific Bentley rules that we talked about last time, some of these are easier to do automatically than others, especially at the relatively low level of abstraction of C code. So looking at our list, it turns out that, most of the clever data structure reorganization things that we talked about, those are a bit out of scope. Those are possible for compilers to do with even higher level languages, but at the level of C, the language semantics kind of specify how stuff's laid out in memory and make those sorts of optimizations more difficult to pull off. We also saw a bunch of examples of different optimizations on loops in code, and why that was really important, because loops are the things that tend to dominate the runtime of our programs. And indeed, out of the example loop optimizations we saw, actually, the significant majority of these compilers, like the LLVM that we're working with, can do these to some degree. So hoisting code outside of loops that's invariant to the loop, that doesn't change over the iterations of the loop, totally something a compiler will do, and it's a nice thing to be able to rely on. Unrolling loops to varying degrees, definitely something a compiler can do. Fusing multiple loops at the level of LLVM, it's possible to do that somewhat. More complicated examples, may make it not safe to apply that kind of rewrite, but we can get some optimizations via loop fusion and eliminating wasted iterations. Similarly, sometimes the compiler can be clever enough to do that. Of the logic optimizations we saw, again, this is exactly the kind of stuff that with a couple exceptions that our compilers are designed to give us. So constant folding and propagation, eliminating common sub-expressions, rewriting arithmetic expressions based on simple algebraic identities, short-circuiting code to some degree, how we order tests to be most efficient, combining tests into clever switch statements or other things. That's all stuff that our compiler is actually pretty good at. Similarly, working with functions, at least some of the basic optimizations, in particular inlining and in some cases tail recursion elimination, are things that compilers can do. Coarsening recursion is, again, something that's hard to do at the level of C. And it turns out there's also lots more optimizations that our compilers can do beyond just these. So for example, effective register allocation is a really big part of the compiler's job. In C, we don't reason about the physical registers that our machine has. So packing all of our intermediate results efficiently into the limited number of registers that x86 gives us is a big part of the compiler's job. And then we'll see a bunch of these other optimizations further on today, including things like promoting values from memory to store them in registers. The logical abstraction that C gives us is actually that basically every value is living in memory somewhere, either on the stack or in the heap. And every time we assign a value, we're updating it in memory. But frequently we'd like to never bother touching memory at all and just store intermediate results in registers. So figuring out when that's safe and rewriting our code to do that, promoting memory values into registers, is a big part of what the compiler is going to do, which is one of the things that we'll see first. Similarly, there's lots of other loop optimizations down at the level of more computer architecture issues like vectorizing loops, parallelizing loops in different ways in some cases, and other optimizations to the logic and functions, also kind of closer to issues that matter at the assembly code level. One final comment here, it's very difficult to make an exhaustive list. We're only going to touch on a little bit of this stuff today, but a key point is, compilers are constantly evolving. LLVM releases new major versions every 6 months. All kinds of other compilers are evolving all the time too. And new optimizations are constantly being, introduced and implemented. And so, we're never going to have a totally exhaustive list of optimizations, but this is at least a taste of a lot of the stuff that you can expect most modern compilers to do. All right. So now let's dive into some of these optimizations in practice. But before we go too far, I've said so far that most of the optimizations are applied at the level of the LLVM IR code. We talked about the optimizer being a pipeline that takes in LLVM IR from our language front end and then applies a series of passes that rewrite that IR into more and more efficient forms. But we're always staying within the domain of LLVM IR. And it turns out that that's true for most interesting stuff that our compiler is going to do, but not quite everything that the compiler can do for us. Some interesting optimizations also wind up only appearing at the level of the target machine code or the assembly. So these are optimizations down to the level of cleverly using the features of our particular machine's instruction set architecture. And so here I have a couple of examples, so 3 different examples where this is the case. So let's look at these. So in the first example here, so in each case, we're just working with uint32, so unsigned 32-bit integer values. In the first case, we're taking in a value n, multiplying it by 8. In the next case, we're taking that value n, multiplying it by 15. And we're taking the value n and dividing it by 71. And if we look at each of these, we can see the LLVM IR that they translate into after optimization. So in this first case, this corresponds exactly, I think, to one of our Bentley rules or bit hacks. So in this case, the compiler is recognizing that we're multiplying by 8, which is a power of 2. And when multiplying binary integers by powers of 2, that's basically the same as just bit shifting. So we can replace this multiply by 8 with a shift left by 3 bits. That's what this instruction here does. So this LLVM register 0 is holding our input value n. So we're going to shift left the value of n by 3 bits, and that'll give us our result. So that's the kind of optimization I think we expected our compiler to be able to apply. That's cool. We can see that at the level of the LLVM IR. But if we look at these other 2 examples, there's really nothing very interesting happening. So here we said y is equal to n times 15. In LLVM, that translates into integer multiply of n by 15. It looks basically exactly the same. Similarly, z is equal to n over 71. We're going to do an unsigned integer division of n by 71. So there's really nothing clever happening here. So at this level, it looks like the only clever thing we can do is in that first case, and everything else just translates directly into equivalent operations in LLVM, the multiply and the divide. But if we look at the x86 assembly that gets generated, it turns out in each case, it's actually doing something even more clever than what the LLVM IR showed us. Let's take a look at these examples one at a time. In this first case, we had x equals n times 8. The LLVM IR had optimized that into a left bit shift by 3 bits, okay? But then we see what that becomes in x86, and it's LEAL of something and puts it in the EAX. There's an 8 here, but it's not quite clear what all is going on. Okay, so what is this even doing? So it turns out this LEA instruction, I don't expect everybody to memorize these things. LEA stands for load effective address. And this is a particular kind of unusual instruction in x86 that lets us take an addressing expression, so a memory address expression, like we would normally have if we were using an operand from memory in some computation. But then instead of actually loading that value from memory, it just computes the address, what the effective address would have been, and stores it in the output register. So in this case, we're computing the address of this somewhat complicated addressing expression. This is using that that like most complicated, I'm forgetting the name already, the like strided, base extent stride addressing mode, the most complicated addressing mode we talked about a couple lectures ago, using that to compute some address based on our input n and store it into EAX. So understanding what that LEA instruction does, can anyone tell me how this might be working? And maybe also why we would want to do it this way? Does anybody have any thoughts? A couple guesses maybe coming in. Yeah, great. So Anthony observes that we're computing the address corresponding to RDI times 8. So that's exactly right in terms of how this is working. So RDI was holding our input value n. This was kind of abusing that fancy addressing mode, which has the ability to do a small power of 2 multiplies for different strides. I think this the base here is defaulting to 0. Our index is RDI, and that's being multiplied by a stride of 8. So we're multiplying by 8 using the address calculation syntax. And the reason for this is exactly what a few people have raised. It turns out that there's dedicated hardware in our processor pipeline, so dedicated ports, execution ports, specifically for computing memory addresses. And those even have optimized ALUs for doing these small power of 2 scale factors. So there's dedicated hardware off to the side of our main ALUs that can do a simple operation that happens to be equivalent to n times 8. And so the back end of our compiler decided to do that. All right, so now let's look at this next example. So we started out with y equals n times 15. At the LLVM level, we saw that still just became y equals n times 15. But at the x86 level, we now have 2 of these LEA instructions. So we're taking in our input RDI, that starts here, and we're working our way through the RAX register to ultimately get the output. But, 15 doesn't occur anywhere here. And in fact, we don't even have multiples of 15 here, or divisors of 15 rather. So does anybody have ideas about what this is doing? How this is working? Yeah, great. So the observation, which a couple people just made, is that this is breaking down multiplying by 15 into 2 of these clever, use the address pipeline to do math for you tricks, where we first are multiplying by 5 and then multiplying by 3. If we think about how that's actually working, what's going on here is this remember, is base plus index times scale gives us our ultimate address. So here we have n plus n times 4, that's equal to n times 5. We store that in the output as an intermediate. And then we take that intermediate, again, plus itself times 2, which is ultimately times 3. So we've broken it down into this clever abuse of our addressing hardware to multiply by 5 and then multiply by 3. But we saved our integer multiplier for doing more complicated things. Cool. All right, now this last case is even weirder. And I don't really expect anybody to be able to figure out exactly what's going on here, but does anybody have any guesses? So we were trying to divide n by 71. And what we see is I guess we make a copy of the lower 32 bits. We store some magic number in another register. really big magic number. We multiply them, and then we shift back by 38 bits. So the guess here is our 71 and our big constant inverses mod 2 to the 32. And that's a good guess, but it's not quite it, I don't think. It's related. Now, it doesn't matter that you understand this in detail exactly, but it turns out this big magic number is, we often actually call a magic number. In this case, it's equal to 2 to the 38 divided by 71 plus 1. And what we're effectively doing here is moving from the world of binary integer representations to what's called fixed point numbers, where instead of all the bits of our number representing 2 to the power 0, 2 to the power 1, and so on, so we're representing whole numbers, we have we split our number in half with what we call a binary point. And on the left side of that binary point, the digits represent 2 to the 0, 2 to the 1, 2 to the 2, et cetera. On the right-hand side, they represent 2 to the negative 1, 2 to the negative 2, 2 to the negative 3. So they effectively represent fractions. This is different than a floating point representation because that binary point location is fixed. And it turns out that integer on fixed point numbers, arithmetic on fixed point numbers is almost the same as arithmetic on integers. So we're able to abuse our integer multiply. And this constant is equal to, if we shifted our binary point to 38 bits into our number, we represent the fraction 1 over 71. So we're multiplying by the fraction 1 over 71, and then shifting those 38 bits back down to the bottom. So kind of a crazy trick, but this is all stuff that your compiler can do down low level. If you'd like to see more stuff like this, there's a really great book called Hacker's Delight that you should check out. It talks about how to derive magic numbers like this and lots of other cool low level tricks. It's really pretty fun. All right. So with that, now I want to pop up a level and start talking about what our compiler is actually going to be able to do to optimize more common code at the level of LLVM-IR. So I want to start looking at what we can do first with simple scalar arithmetic. So let's say that we have this C code. So we're just defining a function that multiplies two numbers. So we take in a double precision floating point number A and another one B. We multiply them and then we return the result. So this is about the simplest floating point C function you could imagine writing. Now, what happens when we compile this without any optimizations? So down at optimization level 0. Turns out Clang is going to spit out LLVM-IR that looks like this. Okay, so we started with a really simple function and we wound up with something that seems to be significantly more complicated. And it's not totally obvious what's going on here. If we look down towards the end, we can see our multiply and our return. So that's pretty much what we expected. But why do we have all this other stuff here? Does anybody have any guesses what's going on with this? Why is there's this big blob of code before we actually do what seems to be the main work of the function?
It is to protect the.
Can you put the answers on Slack?
Oh, sorry.
It's okay. Yeah, some guesses. It has maybe to do with something with the calling convention, like C is call by value. Floating point arguments are passed through different registers or something, or maybe there's some casting going on. It turns out that's all sort of related, but not quite it. Really, what's going on here, you could have easily written a C compiler only capable of compiling a function like this without having all this other crutch in the middle. But Clang needs to be able to compile completely arbitrary C code. And it would like to be able to do that using fairly, logic that's as simple as possible. And it turns out that the semantics of C are really complicated. And like I alluded to a while back, one of the key aspects of the C semantics are that basically every variable that we have logically has to live somewhere in memory, unless we can prove that that there are no ways that any other code could have seen it in memory. And so what the compiler is doing is it's adopting a really conservative approach to generating very straightforward, correct code. It basically says, okay, C is a simple stack machine. All of the local variables in any function are just going to be allocated on the stack. And then anytime we use them, we're going to load them from the stack, do computation with them, and store the result back to the stack. And I'll unpack it in a minute, but that's basically what's going on here. But now clearly that's not necessary in a case like this. Unfortunately, if we turn on any optimization in our compiler, so here we're just doing -01, that all gets simplified away almost immediately. We wind up with simple code that's a lot easier to read and think about. So now our LLVM function for multiply looks basically exactly like we'd expect from our C. So we just take the two arguments, multiply them, and then return the result. That's all that's happening. And one side comment here, even if you want to understand the basic IR that comes out of a function, out of some C code before the major optimizations, it's often useful to look at it at 01 rather than 00, just because it gets simplified so much. So it's not going to, at 01, it's not going to do really fancy vectorization and loop transformations and all kinds of other stuff like that. But it will take all that, really messy, verbose gobbledygook where everything's just being loaded and stored off the stack all the time and flatten it into much simpler straight line code that's often a lot easier to read. So if you want to look at basic LLVM IR to understand what some C code generates at a basic level, I think often using 01 instead of 00 is a useful starting point. All right. Now let's see quickly how the compiler actually optimizes the original code to get here. So remember, this is actually what the Clang front end is generating, this more verbose code that we started with. The Clang front end is responsible for taking the C code and translating it in LLVM IR, and it does it in this kind of dumb, conservative way that generates all this extraneous stack memory manipulation. And I roughly alluded to what's going on here, but if we unpack it line by line, what we can see is these first two lines are indeed allocating storage for the local variables on the stack. That's what the alloca instruction does. Then we're using those, so 3 and 4 now store the addresses of the memory that we've allocated to store those local variables. The next two lines take the arguments and save them to those stack locations by storing them into memory. Then we're going to turn right around, load them back from memory, do our actual multiply, and then return the result. Now, again, like I said, if you're only dealing with code that's this simple, this seems needlessly overcomplicated, but it turns out that this strategy is really easy to generalize to other code that's more complicated than this. But obviously, in lots of cases, it does tons of unnecessary work. So one of the first things we want our optimizer to be able to do is be able to eliminate all this stuff. So how might we do that? So the good news is we can actually optimize all this away pretty easily. And the basic idea is just to, and this is often done by the memory to register pass in LLVMs. You'll see references to mem to reg. That's this core optimization that we have in step 1 here. And the basic idea there is to just say anywhere we have local variables being loaded off the stack, check whether it's possible to trivially know what value was stored there and just use those values from registers instead of rereading them off the stack. So in this case, we have the first argument, first operand, our multiply is register 5. And we see that that's being loaded from memory address 3, the memory address stored in 3. But if we look back, we can see all we did you know, what's in 3 was just stored right here from register 0. You know, there's no branches or control flow here, so there's no way that something else could have gotten into that memory. All we did was allocate the memory, store register 0 into it, and then reload it into register 5. So what if we just replace this reference to register 5 with the thing that we'd stored in memory, which in this case was register 0? That's the first step, and that's basically the mem to reg pass. And then the second step that goes right alongside this is to now remove dead code. So if you look in this case, now nobody's referencing this value that was loaded into register 5. So that's dead. The store that put the value there also can't be seen by anybody. And the actual memory allocation that allocated that stack location has become irrelevant. You know, no other code interacts with these things. So those are all dead. We can delete those. All right. Any questions on this? Does this idea make some sense? Maybe one question coming through. Maybe I may come back to it in a bit. So, all right. So now, you know, obviously we can do the same thing again. We had 2 different things stored on the stack here. So again, we can look at register 6, see the same opportunity to do a mem to reg promotion. So we replace it directly with the argument register 1, and then we can eliminate all the dead code. Now, once we're done with that, we see the output that we got out of -L1. So again, now our multiply just directly takes its 2 arguments, multiplies them, and returns the result. Great. Right. And the question raised is, what if some computations are performed on the register such that it's not obvious that the local variables can be replaced? This is at some level a complicated question. I'm not sure what exact operations you're imagining being applied on the register. One of the key things about LLVM IR is that that I think was covered last time is that it's in what's called static single assignment form. So the registers are always immutable. What we talk about is these registers. They're different than machine registers, which can be updated over time. So each of these registers actually refers to a unique kind of immutable value. And so we can always uniquely identify kind of what's coming where. There are more complicated code patterns you could have. If we had control flow here, it might or might not be obvious whether the value loaded from memory at a given point would always be coming from a specific other value. But that's some of what winds up making these analyses more complicated in practice. But the real implementation, the mem to reg analyses in LLVM is actually very powerful for reasoning through quite complicated structures that emerge in real C code. So most of the time you'll see this stuff take effect. All right. So now let's actually, excuse me for 1 minute, take maybe give you guys a momentary stretch break. I need to grab a glass of water because my voice is getting a little hoarse. All right, back again. Okay. So that was a simple example of optimizing this with scalar code. So now I want to think a little bit about what we can do with code that has slightly more complicated data structures. Okay, so let's now imagine that we have this C code. So we're defining a very simple struct type called vect that has 2 doubles. So it's just storing 2 numbers, X and Y. we have three local variables, A, B, and C, that are these 2D vectors that we're storing on the stack. We maybe do some computation with them. Somehow we wind up with values in A and B. And then ultimately we say that the structure C is going to be equal to the element-wise sum of A and B. So the X value of C, which is the first field, is going to be AX plus BX. And then the Y value of C is going to be AY plus BY. Okay, so just very simple C code using structures, in this case to represent 2D vectors, which is something you'll wind up seeing actually in some of your different assignment code. All right, now this is the LLVM-IR that Clang initially generates. So it's a bit overwhelming at first, but let's unpack this a little bit. All right, so at the top, we again see our structs allocated on the stack. And it turns out that they're allocated in a slightly weird order. So register 5 is the address for the struct C, and then A and B are put right after that. Okay, then our ellipsis corresponds to an ellipsis, and we get down to the code that is going to do the actual work for this function. So here we see a whole bunch of get element pointers, loads, get element pointers, more loads. And then if we squint in the middle, we can actually see an add happening and another add happening and storing the results somewhere. So if we unpack that a little bit, what's happening first here, this first get element pointer instruction is computing the address of the X field of C. So that's index 0 is the first field, which is the X field of the struct. So remember, %5 is the local variable for the struct C, and we're indexing into it to grab field 0, so that's C.X. Then we're indexing again into the X field of now a different struct, the struct stored in register 6, or whose address is stored in register 6, which is A.X. And then we're loading that value. We're loading from that address. So this pair of instructions loads A.X. Similarly, we see the same thing to load B.X. Then we take those two values that we loaded out of the structs in memory, store them, add them together, and then store the sum into the address we computed first for C.X. All right. And then we repeat this for the second field. So here we're looking at the Y field. So it's index 1. That struct index 1 is the second field, which is Y. We're doing all basically the same thing. So C.Y is equal to A.Y plus B.Y. All right. So you can see this code is actually, winds up getting a whole lot more complicated, because not only are we working with values allocated in local stack memory, but those values are being packed and unpacked, and we're doing complicated addressing calculations to pull them in and out of structs. And this winds up making the code a lot harder to optimize because we have a whole large number of different operations that actually operate on the individual fields of these structs, but it's all being indirected through having to compute the offsets of those things in memory. So one of the other key optimizations our compiler can do is what's called scalar replacement of aggregates. And the idea here is to bust up these aggregate structures into individual fields, and then just work with them at the level of those individual fields and optimize the code at that level. So if we go back to our to the code that we had before. So if you imagine that A.X and A.Y are originally set from registers 0 and 1, say, respectively, then where we have a use of A.X, so we're going to be doing the same thing we did in the scalar code before. We're loading from somewhere in memory, which corresponds to A.X, and then using that as the first operand to our add. But what if we try to play the same trick that we played before with the memory to register promotion? then we're going to, because we knew that the value stored in a.x comes from register 0, we can just replace the reference to the load from memory with the reference to the original register 0, which means that load is dead, which means the address calculations are dead. And we've simplified all that away. We can do the same thing for a.y, replace the load or the value that was loaded from the structure in memory with the original register value that was stored there. The load dies, the address calculation dies, and we simplified things kind of along the lines of what we did in the first example. At this point, our entire struct A that we allocated in local memory has become irrelevant, and we don't need to worry about it. So we can do the same thing, not too surprisingly, with B. So b.x, imagine in this case, b.x and b.y are originally set from the registers 2 and 3 respectively. So now where we immediately use a load from b.x, we can just replace it with register 2. And all the code that we had to get it from memory is now dead. Similarly, b.y can be replaced with register 3, saving us a bunch more code and saving us another local allocation. All right. So that's basically what we did before. And we can see that that same idea applies if we start reasoning about the fields of structs as individual things in kind of the same way. So our basic mem-to-reg optimization will get us that far. But what about C? So, with C, it's not really clear how we want to represent this aggregate value that we potentially want to pass around as a whole thing. So we might, return the struct C, for example, or pass it as an argument to another function. So we want to be able to carry around the whole value. And currently, the only way we have of doing that is by passing pointers to it in memory. But the key idea here is to exploit additional features of LLVMIR that let us represent values that are struct typed. So effectively, in our underlying machine, our registers just store 32 or 64-bit integers and floating point numbers and stuff. So you can't store a struct meaningfully in a register. But at the level of LLVMIR, there are features that let us do that. So these virtual registers we're working with at the LLVM level can store actually complicated aggregate data structures. So in this case, we're going to, instead of storing the values of the C struct in memory, we're instead going to insert them into the two fields of a struct of the same type, a struct that consists of a pair of doubles that we're going to store in virtual registers. So here we're inserting the value %14. Oh, sorry, I think that might be a typo. It should probably be %19. Where it's inserting C.x into the zeroth field, the X field of this structure, and we're inserting the register 25. So that's the sum of AY and BY into the second field. Okay, and then once we've done that, again, we can eliminate a whole bunch of memory and address calculations and the actual allocation by which we were dealing with the C structure. So once we're done with all this, we've effectively eliminated all the memory manipulations, not just in the case of simple scalar code, but also when working with structs. Well, any questions about that? All right. So now I want to talk a little bit about optimizing function calls. So to do this, I want to look at a slightly more complicated example. So in this case, we're going to look at a simple n-body simulator. And so the problem here is we have a two-dimensional world made up of n point mass bodies. And those are moving around in 2D space under the influence of gravity. So each of the endpoints is tugging a little bit on each of the other endpoints according to simple simple law of gravity based on, as a function of their mass and their distance. And we can represent that in code at a high level using something like this. So first we have a data structure with which we're representing each of these bodies. So just like before, we have a simple vector, 2D vector type to represent the position. We also use vectors to represent the velocity and force on each point. Then we have a scalar value for the mass of each of these bodies. And then if we have that, and we pass in an array of bodies, the size of the array, and the number of time steps we want to apply, and how big a time step, what time quantum we want to apply, then the whole simulation can just be represented at a high level by this simple for loop. We're going to say for each time step, first we calculate the forces on all the bodies, and then based on those forces, we update the positions. Fairly simple simulation algorithm. All right. And these top level methods are going to invoke a bunch of simple routines on 2D vectors. So everything we're dealing with here is in flatland. So we're doing physics in 2 dimensions. So 2-dimensional vectors are going to be really common quantities we want to work with. We'd like to be able to do simple math on them, like add vectors together, scale vectors, compute their length, or in this case, their length squared. So imagine we have a bunch of kind of helper routines or methods that let us do that. So we can add 2 vectors together by computing the element-wise sum like we saw before and returning it. We can scale a vector by a scalar by multiplying each of its elements, or we can compute the length squared, which is useful in our gravity calculation. All right, and then kind of the meat of the work is going to be updating, calculating the gravity and calculating the forces and updating the positions. So this is the function that updates all the positions. But for right now, I just want to focus on this inner core code where kind of the meat of the update happens. So this is where we compute the new position after our time step as a function of the velocities in previous positions. So, we can see what we're actually doing is taking, like in more detail, we're taking the previous position. Actually, maybe it's easiest to dive all the way in. So we're updating the velocity vector based on the new gravitational forces. We're scaling that by the size of time step that we want to take, and then adding that to our position. So we're taking a step along the velocity vector from our current position based on the time quantum. All right. So now let's look a little bit at how the compiler actually generates code for this. So after we apply lots of other optimizations, we wind up digging into this code and seeing that under the covers, this scale call does does roughly what we'd expect. So we're going to be extracting 2 values, multiplying our time quantum, like extracting 2 values corresponding to an x and y of one of the vectors, multiplying our time quantum by 0.5, which is the slightly optimized way of dividing it by 2. And then using those values, we're going to call the vec_scale function. All right. So that's the code we had at the point at which we called vec_scale in our update position routine. But then if we look inside vec_scale itself, it's actually really, really simple code. So it was just multiplying 2 values, packing those back into a structure and returning the result. And so, the issue here is we'd like to have our code be abstracted so that we're able to write these different operations like vec_scale as a library of different helper routines. We don't have to explode them all into individual scalar operations everywhere we want to use them. we can use those simple functions to help us write more concise high-level code. But the problem is that function calls have overhead. And if all we're doing is multiplying two numbers together, that overhead can really get in the way. We're probably going to, if we literally make a function call to multiply two numbers, we're probably going to be spending significantly more time dealing with function call overhead than doing actual useful work. And even beyond that, the function call can kind of get in the way of different optimizations. It might be possible to do some arithmetic simplification, or like algebraic rewrites, common subexpression elimination, or other things, if we actually unpack all of these operations and could look at them all together. But if we hide them all behind function calls, it's harder for our optimizer to be able to see what's going on inside. But there's a useful optimization we can apply in cases like this. And the idea is, since the code for our vec_scale function is really small, why don't we just copy and paste it into into the call site? And this is what we call inlining. So we have this really simple vec_scale function and the place where we called it. So we can literally copy the code from vec_scale into place and just use it directly. So we're just taking the body of the function and just using it directly. At that point, if we want to make this all make sense, we need to actually. I think there might be a typo. Oh, no, I think it's all right. Sorry. The return statement from our function obviously has become irrelevant, and also the call to the function has become irrelevant. So now basically we want to take, everywhere that we previously referenced this register 27 that was the result of the call. Now we're just going to reference this register 29. That's the output of just doing the same thing that function call would have done right in line in the code. So that, once we've inlined, we get code that looks like this in the core of our update positions routine. But if we look a little bit further, if we step a little bit further out in that higher level function, so here was the basic code that we inlined. But if we look at what we were doing immediately afterwards in the higher level function, we were immediately turning around and extracting those values back out of the struct. So what we've wound up with is, we had a function that returned a vector and a struct, and so it had to pack its two scalar values into a struct. But then that returned it to higher level code that just immediately extracted those two values so it could compute on them. So the next idea here is, like I said, inlining can enable opportunities for further optimization to be applied to our code. So in this case, we see this redundant sequence of packing and unpacking, and we can just remove useless operations like this. So if we then look at this entire core update that we were thinking about, we had three main function calls. We have a vector add, of a vector scale, of another vector add. So if we step out further in the code, we have two more function calls. Another one. So we were just inlining the vector scale. We can see that we have this inner vector add is another function call, and this outer vector add is the final function call that we do to get the ultimate result. So why don't we inline this as well? And then, remove the corresponding useless instructions to, again, you can see, more instances of packing and unpacking values from structs. And it turns out that, once we do this, of inlining each of these function calls and applying all of this scalar replacement of aggregates, the ultimate code we have for this core update just looks like this. We started out with C code that did a whole bunch of function calls and was passing structures around. And under the covers, we wind up with basically the dense code that we would most ideally like, just doing the raw adds and multiplies that we actually need to get this work done. And if you step back, you can think of that as basically being kind of equivalent to C code that looks something like this. So we're taking every single one of these, complex expressions that we hid behind a function and unpacking them into simple statements that we just do one after another, all inside our one main function. And as you can imagine, doing that instead of actually making the calls is a lot more efficient. But the problem with writing code like this is that it's a lot harder to read and modify. We've basically thrown away all our abstraction. So if we had to write code like this to make it go fast, writing efficient code would be a much harder problem, and efficient code would be a lot uglier. But the good thing about the compiler being able to do a good job, of optimizing code in these sorts of cases is we can get the performance of this messy inline code while still writing simple, clean, abstract code. And function inlining is kind of the key optimization that lets us get that benefit. All right. So now quickly, why doesn't the compiler just inline all function calls? It seems like, I was saying there's overhead to function calls. Why don't we just inline all of them all the time? Does anybody have any ideas? Great. I think people hit on the two biggest, immediately hit on the two biggest reasons. So Elizabeth said recursion, Anthony said the executable will be large. Other people getting on things related to the executable being large, like having lots of instructions and that overloading the instruction cache. And that really gets to kind of the two big problems with inlining everything. So first of all, it's not actually even possible to inline all function calls. So if you think about if we have recursive functions that call themselves, what would it even mean to inline them? If you have a program that can recurse a potentially infinite number of times, you need an infinitely large inlined program in order to flatten it all out. But it turns out that even in the cases where you don't have recursion, there's potential overhead to doing this inlining. And that's because it makes the resulting code a lot bigger. So if you have many different parts of your code that call the same function, inlining is going to copy it. If I have n different calls to the same function, inlining is going to make n copies of it throughout my compiled binary. And like we've talked about a few times before, sometimes that can be a good idea, but sometimes it can make things slower or less efficient, because having really, really big program code means like our instruction cache doesn't work as well. It means the penalty of mispredicted branches is going to be higher. And so internally, so fundamentally, there's a trade-off here. And it turns out that there's also some additional difficulty in that if we think about how our C compiler toolchain works, we're compiling individual C files separately all the way into machine code. And then we're just resolving the function calls between those later at link time. And so, what would it even mean to inline code from one C file into another one? It turns out that, the classical way C compilers work, they can't do that. They don't know anything about what's going on inside those functions that are written in other source files because they're being compiled at a separate time and maybe even a separate place. Modern compilers like LLVM do support optionally what's called link time optimization, where they first will build the IR for all the different C files and then put them together and consider things like inlining before generating the machine code. But that's not always possible. All right, so inlining can be a good idea, but sometimes it's also prohibitively expensive or might explodes the size of our binary. So how does the compiler know whether or not inlining a function is going to be a good idea? How do we know whether it's going to help performance or hurt performance? And the short answer is, like most of the optimizations we're looking, that our compiler is actually going to do, it doesn't really know. All it can really do is make a best guess based on heuristics. Fortunately, these heuristics often do a pretty good job, reasoning that simple small functions that aren't recursive are probably worth inlining, and functions above some threshold size maybe aren't. But fortunately for us, it's also possible, in cases where the compiler doesn't do what we want, inlining the code the way we'd hope. There are also a bunch of annotations we can put in our code to control whether inlining does or doesn't happen. And in particular, in the C standard we're working with, you can apply attribute always inline to a function to tell the compiler it should always be inlined, or the attribute no inline to tell the compiler, please don't inline this, I don't think it's a good idea. these are attributes you may find yourself wanting to use in order to balance between creating good abstractions in your code and still getting high performance, nicely inline straight line code in your critical inner loops. All right. So now, speaking of loops, I'm probably only gonna have time to touch on this quickly, but I wanna briefly go over the last key optimization that it's really important for our compilers to do, which is optimizing loops in our code. And we're gonna do this by actually looking at a parallel loop example. So here we're not using just a regular for loop, we're using a silk for loop, which we talked about a few lectures ago in the matrix multiply example, and we'll see more later when we talk about parallelism. But this is roughly similar, you can read this as roughly being equivalent to just a standard for loop. And what we're doing here is computing the norm of an input vector. We're normalizing a vector by dividing it by its norm. So the core computation here is to compute the norm of the vector, divide each element by that norm, and then store that in the corresponding element of the output. What the silk for means, again, is that it's basically like a normal for loop, but each iteration is independent, so we can do them in parallel. If we step back and look at the IR, this is similar to examples that TB showed last time, but with some slightly more complicated extra annotations related to parallelism, which we'll introduce later. So we have some loop control at the top, and again at the bottom with a back edge going back to the top, and then we have the main loop body. The specific details of how this parallel control works we'll cover again in a few lectures. And there's lots of other details kind of hidden away inside this code. But as we saw last time, we can ask LLVM to draw the control flow graph of this function. And if we do, we see it's pretty big and complicated. And so looking at LLVM IR as we have been so far, I think actually obfuscates the basics of the sorts of optimizations we want to understand here. So for this discussion, I'm just going to look at simple pseudocode that corresponds at a higher level to the rewrites that the compiler is going to be doing. So the first big optimization the compiler can do in this case is recognizing that this call to norm always returns the same value. So for each time we go around this loop, we're just computing the norm of the same vector. So x isn't changing in this loop. So the norm of x is always going to give us the same answer. So it'd be really nice if we didn't have to compute that for every iteration. And it turns out that the compiler can do that. So we can do what's called loop invariant code motion to hoist this norm computation outside the loop, store it in a temp variable, and then just multiply by that each time we go around. So there's an additional little trick going on here where instead of keeping the divide, we're doing the division ahead of time in addition to the norm computation. The division is more expensive than multiply, so we take the inverse first and then just multiply in the inner loop. Okay, now the second big optimization here is related to something else that we saw in our matrix multiply case study. And if we look at what's happening inside each iteration here, these are actually really fine-grained scalar computations. So we're just loading a single value and doing a single multiply for every iteration of this loop. And there's a lot of overhead, even for a sequential loop, but especially for this parallel loop. So since the loop isn't doing much work per iteration, the next idea is to coarsen this computation so that we can do more work in the loop body. In this case, splitting off chunks of 2048 iterations, which we're then executing in parallel. This is called loop strip mining. So we've coarsened the outer parallel loop kind of along the lines we talked about in the matrix multiply case. But in this case, the compiler's chosen grain size to use. It thinks that's the 2048 inner elements is going to amortize the overhead of the outer parallel loop. And then, it has to deal with a little bit of extra detail at the end, because not every n is going to be evenly divisible by 2048. And so we have to do a little cleanup at the end where we take any additional fractional iterations that would have been left over and compute those. So I think that's all we have. Oh, actually, I guess I could quickly touch on one more thing, which you'll dig into more in the homework. So part of the reason we did that coarsening optimization was to reduce parallel overhead. But another reason is that now we have a simple constant size loop that the compiler knows how to vectorize. And so once we have that, hitting it with our big, loop optimization hammer, ultimately the inner code can be really fast packed vector AVX code. The compiler also implements, lots of other things at the level of, rewriting loop code of different forms, but we don't have time to go into more of it today. So I'll just leave you with that for now. There's a few more examples in the slides that I'll post online, and we'll move on to other stuff next time. Thanks.